Everybody, let's spend a little bit of time talking about metallic bonds and what they are. Uh, it's kind of funny because metallic bonds, we spend a lot of time in chemistry kind of avoiding them, at least in lower level chemistry classes. But I think they're really unique and it's really kind of a, I don't know, I don't want to say that it's super fun to talk about. It's not like you're going to sit at home and talk to everybody at home about metallic bonds, but they're different. They're different than covalent bonds or network solids or coordinate covalent bonds, ionic bonds. Like, it's a whole different thing. And part of the reason why I enjoy talking about metallic bonds is because it requires you to know a little bit more about the structure of an atom than maybe covalent bonding, ionic bonding, and things like that. Because the nucleus of the metal atom acts independently of the electrons, and that kind of gives rise to all these awesome properties that metals have. So let's get started a little bit talking about this. Let me move forward here, and before we get into anything, let me get rid of my crazy face here because that's what I can do. But let's talk about metallic character. So I'm going to actually exit out of this guy, and then I'm going to go to Web Elements. Okay. Keep in mind, Web Elements is by far my favorite periodic table on the internet. Okay. It's just one of those things that I really love. So in terms of metallic character, what I will say is elements have metallic character by being more metal-like. The more metal-like they are, the more metallic character they have. And that's, I know, I'm not like breaking through with any sort of rocket scientist things, but it's kind of like the opposite of electronegativity. Here we have francium, and here we have fluorine. Francium is the least electronegative element. Fluorine is the greatest electronegative element. And electronegativity is the ability for atoms to gain electrons when it's bonded. Metallic character is the opposite of that, where you have francium. This guy wants to get rid of its electrons more than any other element, and that's what makes it most metallic. And so one of the things that we can do when we're using periodic trends to describe bonding and elements is we can bring up metallic character in terms of this as opposed to maybe electronegativity. The things with the least metallic character, or sorry, not the least electronegativity, which in turn is the most metallic character, the things that are most likely going to form metallic bonds. These guys over here, they don't form metallic bonds at all because these guys are nonmetals. Why are they nonmetals? Because they have the least metallic character. They're the highest electronegativity, and they kind of want to get electrons from everywhere, which is also another reason why we separate the periodic table into nonmetals and then metals, because all of these have a certain amount of metallic character. It decreases as we go across the periodic table, but these elements, including these guys, they all want to kind of lose electrons, or at the very least don't want to have electrons floating directly around them, or don't need to have electrons floating directly around them. These guys, the metalloids, these guys are kind of in between. They could take electrons, they couldn't. They're kind of in between in terms of metallic character, and these guys have the least amount of metallic character, which, when we think about it, is completely the opposite of electronegativity. Okay, so I've beaten that horse until it's dead, so I'm going to go back to, I guess, the guy here, and let's talk about how we get these properties. Okay, so we have properties like conducting heat and conducting electricity and malleable and ductile. And in order to do that, we have to talk about the structure of metals when they bond metallically. So So make sure you write these down because I'm going to talk about them in the next slide when we talk about the structure. Okay, so whenever things are metallically bonded, what is happening is you end up with a whole bunch of nuclei here, okay? And those nuclei do not want to attract each other, okay? They are the same charge. They are like charges, so they want to repel each other. But they come together because these electrons are kind of lassoing them all together. But it's not just this one, it's this one moving and it's this one moving. And the electrons are moving freely here that are kind of lassoing around all of these electrons or around all these nuclei and holding them kind of all together. Okay, and so that's where we get this phrase sea of electrons. Okay, ever since I took chemistry way back when, metallic bonding has always been described as a sea of electrons because this electron, even though it may have originated from here, can move all throughout this whole complex. And here I'm only showing 8 atoms. Imagine if this was billions and moles of atoms long. That means that electron can move from here all the way down and all the way this way. It's free to do that. And so the electrons are kind of freely moving all around, and because there's not a lot of metallic character for these elements. It's enough, the electrons have enough to kind of hold the atoms together, but not enough to kind of be associated with anything. So it's this sea of electrons. And so now when we talk about those 4 properties, conducting heat, conducting electricity, well, let's talk about conducting electricity. What is electricity? Electricity is the movement of electrons. Well, if I take an electron, like let's say I plug something into the wall is a ready source of electrons. If I take an electron and add it here, that electron can now move freely. Now it may not shoot out, it may not be the same one that shoots out over here, but now I've added an extra electron to this sea, and that one's going to chain react to this one, that's going to chain react to this one, and that conducting of electricity is what happens when we're dealing with metals. Okay, and the ones that can do it the best are the best conductors. Okay, gold is a really good conductor, but it's very expensive. So we use things like platinum and copper and things that are a little less expensive. Well, platinum's super expensive, but copper definitely. Aluminum used to be really good, but aluminum, remember, is in that is a metal, but I don't know. Aluminum can heat up a little bit, okay, cause fires. And so when we're talking about malleability and ductility, malleable means that you can take a metal, okay, if I have a block of metal, I can hit it with a hammer. Whack, whack, whack. And you can do this with a lot of metals. Okay, and then what you can do is you can shape that into some sort of shape. Okay, I'm showing a bowl here. Okay, but it could be a sheet, it could be anything. Okay, and that's one of the beauties of metals. Why is that able to do this? Well, let's look at the molecules. Again, the atoms are acting independent from each other, and it's only this loose connection that the electrons are having holding the atoms together. So when you hit this with force, this can kind of shove in here, kind of can float down in here, and really just move. And so it may move a little bit out this way to make a little bit of room, but the electrons, because they're moving all around, are still going to hold it together. So it's really kind of neat, and that's the same thing with ductile. Things that are ductile can be drawn out into wires. Well, why would we need wires? Well, we use wires every day of our life. However much we want to think that we're in a wireless society right now, we're not. Computers, webcams, see, look, webcams, that thing right there is filled with all sorts of wires that are conducting electricity that goes down into the thing that I keep looking down at. Okay, that's all wiring. So that's ductility. Okay, and all of these things arise because the electrons are in this sea of motion. Okay, so So I guess that's the end of the slideshow here. Let's go to the end. Okay, and so there it is, and I hope you enjoy metallic bonding.